So waviness in composites can occur basically where there's a geometry change. So that might be where there's a ramp in the composite or a thickness change around radii and curves, or where there's reinforcements such as stringers or webs. Detection of waviness in composites is pretty difficult. Often standard C-scan measurements won't find it. And then if you do know where the waviness is, then measurement of it is your next best option. And even then, that's quite tricky, as I'll explain as I go through the talk. So the go-to method for inspection of carbon fibre is going to be ultrasound. Ultrasound works really well in the sense that as it hits each ply interface, you get a tiny echo back, but that echo tends to just come back and you don't reverberate in the ply. The bulk wave carries on going through the laminate structure at each interface, sending a little signal back, which we can then use to image the plies in the material. So at the moment, here today, we're using manual measurement of waviness, using rigid or flexible arrays, where the operator manipulates the probe to get a good image of what's going on inside the laminate, and then uses manual cursors to position those on the wrinkles and extract the information that the stress and design engineers might wish to know about the waviness. Here are a couple of examples of different shapes of waviness that you might get in a carbon fibre component, and underneath those are the phase array images. The setups for those images are quite different, so you're using different probe frequencies and different beamforming. So the application is, the setup you use is really dependent on each application. Just to show you a quick example of glass fibre, this is much more difficult to inspect. The glass fibres are more scattering, and generally the material is more attenuating, so we tend to use lower frequencies, and often the plies are quite a bit thicker as well. The parameters that we might be interested in are the sort of wavelength, so from peak to peak, the half wavelength from peak to trough, and then the height of that waviness. And then from those measurements, you can derive a number of parameters for stress and design. So the simplest one you can do is draw a line between the peak and the trough and look at the ratio of the height to width, or the slope, or if you like, the angle of that slope. And those are all parameters that are often requested to be measured. You can also be asked to measure the local ply angles. So some of the stress calculations need this, and so this is shown on this graph here. When you then look at qualifying a waviness technique, that's usually based on physical measurements on the actual components. The inspector will take the candidate inspection process, mark out some areas of where waviness has been measured, record the data from the ultrasound, and the position of where the probe was. Then an independent team will come in and extract coupons from those, perform polishing and micrograph work, and then independently measure the waviness that's in those coupons. So this shows a typical correlation result between B-scan amplitude, B-scan half wavelength, and the ply angle with micrograph. And here we're showing the measurement uncertainty for this data set. So using what's called the coverage factor, we want our uncertainty to be calculated with, in this case, 95% confidence. And so what we can see here is that we can measure something with 95% confidence to, say, for height to 0.29 millimeters, for the width 1.89 millimeters, and for angle to 1.47 degrees. So the measurement uncertainty is really giving you a good feel in this case for how well the ultrasound is performing. So in this case, we're capturing the C-scan data. So this is about 0.5 meter by 100 millimeters scan. So we're capturing that with our robot. And then a couple of seconds later, the ply angle data will pop up. And what we're interested in is these areas at the bottom, the red and blue areas. That's where the wrinkle is. But you can see on the amplitude scan, on the grey scan, there's no sign of a wrinkle there. So it's not showing up on the standard scan. If we do a bit more analysis and just drag the cursor over the angle scan, you can see the ply data on just the raw B scan. You can see the wrinkles there. So this is quite exciting, just to show you what you get if you go for a little bit more severe waviness. So this is now this is actually showing up on the C scan, but even using that data, you can't really get an assessment of severity. You just know there's a wrinkle there. And again, a couple of seconds later, we get the angle data, and then if we analyze that a little bit more detail, you can again see the wrinkles. So Detection actually seems to be feasible now, whereas before it was a bit hit and miss. But we still have this requirement to then measure what's actually, how bad is the wrinkle, and give those measurement parameters that Stress and Design asks for. So here I'm just showing you what happens when we run a live data set. And you'll see I'm going to start moving the cursor here over different areas of waviness, the white spots or the hot spots. And you can see that the cursors here are automatically moving into the correct position for the peak and the trough and the width of the waviness. So it's working quite well, but the key question is it working well enough to qualify it? So we took 60 data sets from a previous qualification program, ran it straight through the algorithm, the automatic algorithm based on local ply angle, and recorded the height and width and the ply angle that, of the peak to trough that the fitting process produces. So this is showing a comparison now of the manual qualification data and the same data processed in an automatic way. And what we can see is that we've removed some of the bias on the height, so the data is generally sitting on the line now better. There's a similar level of scatter in the data, and that's to be expected, I guess. There are many sources of that scatter. And then what we can do is see now how the measurement uncertainty actually looks for automatic processing of this data. We're interested in high-speed inspection of composites using arrays, and also inspection of complex shaped parts like aerofoils. Stringer panels or aerofoils all have wrinkles in them often because they're complex shaped parts or they have lots going on inside. So we're interested in incorporating these processing tools in our automated systems. We also offer this as a software upgrade process. So if you have an existing system and you're creating data, then we can process that data, we can read in different data sets and do this analysis offline. We can upgrade your systems to use our software at the point of capture, or we can provide new systems with this software built in.